Okay, can you see that?
Yeah, perfect.
Yeah. So thanks for having me along to talk today. So yeah, my name is Mark Cocking. I'm the Polymer Additive Technical Lead here at the AMRC Catcliffe site in Rotherham. And I have some examples to whiz through to keep this on track in 15 minutes to do with high-level prototyping and how we've used additive, polymer additive. So just to give you an overview of how this is possible, there's so many examples to choose from. I have 6 today, but we have 21 platforms which are all reside in the design and prototyping test group, which is where polymer additive lives. FTM, CFR, SLA, LCD, DLP, typically. 19 of those platforms can be accessed by any AMRC engineers with training. So that leaves 70 plus materials straight off shelf available to all the engineers across the site. We do it this way because on average at the minute we're printing 300 components a month. Pre-COVID we're up at 800 plus a month. You can imagine having a few people running machines, we can't get that many parts out. It also promotes design for additive awareness across all the engineers, speeds up the research, project delivery, and satisfies the demand on site for polymer, which is high. And on the back of this, what it also does is accelerates the use of high performance materials and equipment by training staff and their knowledge in additive. So on to some examples. So the first example is in machining. So this is a Blisk turbine blade from a jet engine. And here we're looking at a vibration dampening solution. So the black areas at the top, they are an H-Shore material, and beneath we have a more rigid material, which is cupping the bottom of that turbine blade, and the dampener block on the top is pushing down on that blade, sliding forward, dampening the blade beneath it, but also then deforming forward to dampen the trailing blade. Very designed for additive orientated, as you can expect, to make all this happen at once. Here's a more detailed example. You can see on the right what that array looks like when mounted to metallic rings for tap testing, just to look at the vibrations and the frequencies passing through the objects. You can see the design of the touch lock and the dampener there, specifically designed so we can get many of these off. We can change materials quickly. We needed rigidity from the touch lock, but also for it to be adjustable by the machine operator. So that is what leads to the hoop design on the touch lock. You can push it up to the bottom of the blade and lock in position. And then when all that's brought together, you have a fully functioning dampening system, which is a lot more compact than a traditional solution for this. Allows enhanced machine access for the operators, but also far less complex and less costly overall. So a good example of how we're using additive in vibration dampening systems. We're doing increasingly more work in this area, and we're having quite a bit of success in it. But this is one of the images I can share with you. So next example, and these examples all vary across segments. So here we have an airflow test rig, and in the middle of that image, where the paths cross, you can see a metal additive heat exchanger, which is a core of 50 cubed. Inside there, there's as you can imagine, an AM specific exchanger geometry, and these tubes are feeding in cold air and a cool air. And then we're measuring before and after the exchanger just to get some data from that. So the idea here is we're looking at the the virtual analysis of that exchanger geometry versus the physical. So this rig was built in 3 months, and that is again all thanks to the design for additive process and having polymer available. It's designed to give us a benchmark so we can see how far these physical versus virtual results are off, or if they're in line. We used standard polymers, high performance, high temp polymers to achieve this. We used additive design for additive perhaps more in depth with the position of sensors within airflow. So to promote the linear flow that we're after, into the exchanger, we wanted to create a little disruption in there. So some of the elements are airfoil shaped where the sensors sit and so on. So that's a good example of some precise work within the system, but also some more robust polymer fixturing elements outside. So a good mix. And this rig can be very quickly adjusted for different core sizes, geometries. We have all these polymer files stored, and we just make quick changes and reprint and go again. And there you can see a thermal image of the system in action. Onto another example. This is called the Meditel robotic all-terrain triage system. So this is an all-terrain tracked vehicle, which is able to just perform initial analysis and aid to casualties that might be in dangerous or remote locations. You can see, if you look at the end effectors, they're all interchangeable, many variants that this can be molded into. And a bit more on that. So it's a collaboration in this instance between the AMRC and Sheffield Robotics. This system, you can see the size of this. It actually contains well over 100 AM components across pretty much all our platforms that we have, and probably 20 or more materials. Fully functional. You can drive this around. It's been on the moors. It's been to various shows across the country. In this instance, the design for additive was coming in strong with the bespoke medical toolboxes and the kits that can be interchanged, and different implements or end effectors printed and put in for specific situations. And it's possible to adapt all that and maintain that system in field using additive manufacturing in remote locations. All VR, AR controlled. That's not my world. My world's more mechanical. But yeah, you can drive this from sitting wherever the operator is. So there's a lot going off here, and with all these things I'm showing you, if anybody did want any more detailed information, you can always contact me for that. So on again, another application for electrification. So this is an air-cooled motor jacket for an electric motor. In this image, a bit of an artistic close-up, but you can see some quite complex geometry here. And this is, again, heavily pushed towards design and additive manufacture to achieve it. You can see better on the next image on the right what's happening internally. So this is a lightweight air-cooled direct drive motor. So air circulates throughout the walls, but also through that base where all those small stanchions are. It's a lightweight eVTOL application. So this is for small personal aircraft. It's got a very complex internal support structure. So we couldn't have any supporting structure inside this at all. So every feature in there is there for a reason. And of course, it's all self-supporting. So that just using Polymer to do that helped verify the design for additive manufacturing approach that we took with this. We printed many versions of this, and obviously they all have to be successful. This isn't a one-off. There were probably 5, 6 or more of these, and they were used for verification of airflow through the system. And ultimately, what we did by using Polymer here is reduce the risk of failure when ultimately this was printed in metal, and obviously the costs associated with that. So a big success on this project for Polymer, another tick for Polymer. And next, just to show that we work, this is Sheffield University, which I'm a part of, but other universities as well, and to aid learning of students and research. So you can see here that this is actually a competition to come up with a Martian rover. And the element we're concentrating on here are the black wheels. They're not tires, they're like solid, but that's what we printed and supplied. So this is a competition where they run several missions across all sorts of different terrain, simulating a Martian landscape, different aggregates, sharps, soft sands, etc. These wheels were printed using a LCD mask resin system. Again, design for additive was considered in this, but in a way, it's sort of, you can see it's a self-supporting geometry. In this instance, we needed a durable resin, so we went for a BASF resin, one of the durable versions that they have. Performed incredibly well. I think everybody on the team was surprised. I don't think I was surprised because I've worked with this stuff before, but given the weight of the vehicle and what it's doing, they held up incredibly well. And I do always like to force this point across when we speak to research partners, like, the material characteristics have really improved over the years. So 6 countries, 14 teams, they placed well, and they're working on the next rover now, and we're going to be doing more prints for that one. So looking forward to doing that. And then I have, I think, one more example, which I thought everybody would quite like. And it's talking about SMEs. So we at the MRC, and I know other networks do as well, we support hundreds of SMEs every year, and polymer additive plays a massive part in supporting those SMEs. In this example, we have a bottle of relish, which has been tested on a proof of concept rig. And we did some flow analysis on the nozzles, and we printed all those nozzles again using polymer additive, and we switched those out, checked flow characteristics, etc. And I think it's really important to recognize that towards these, we always talk about high value sort of applications and so on for large industry, but typically SMEs, they can get a lot of value and a lot of impact and make big strides from what polymer additive can provide them with. So yeah, we do like to work with SMEs and help them out and help them adopt the technology as well, and give them that mindset where when they leave us, well, hopefully they continue with us, but if they do leave us, then they go forward and buy a machine and come up with their own use cases. And that's the end of the presentation I've got today. Hope it was interesting.
Thank you very much, Mark. Here's your virtual clap from me and from the rest of the audience. I'm delighted to see Henderson's relish appearing in a presentation today. I thought
it'd be nice to give a nice light end.
Yeah, any of the Sheffield people here will have been instantly excited by that. Certain. So just while I check to see whether there's any questions in the chat, I will kick off with one if that's okay. Because I loved your Meditel example. And you said, over 100, I think this was right, over 100 polymer AM components across all the different platforms you've got. Yeah. How easy is it for you guys to choose the right platform for the right one of those components? Like how do you go about doing that, or what are the things that help you to decide which ones to use? Yeah, it's always one of the key questions, isn't it, from everybody who comes to you. I think it's part of this network that the reason I did the first slide on how we train engineers is because the tasks within our research centres are so varied that people find their niches in certain areas. So the electronics team, the digital team will understand materials that suit their environment, and then the mechanical engineers, they'll understand like carbon fiber filled materials and so on and so forth. And this is many engineers working on here, so it's not so much like we will go through a parts list and decide for each one. It's more that the experience has been gained by the engineers by continuously using the equipment, and they're doing this down select. I mean, I tend to get involved when things get a little bit more technical, but for a lot of the parts on the Meditel robot, you've got brackets, you've got things that carry circuit boards and so on and so forth. So a lot of this actually just passes through my department, but actually I don't get to touch it. But yeah, I would say the selection of material just comes down to engineer experience. Yeah. Mm-hmm. Yeah, which is why it's great to see you guys looking at training and kind of working with new people as well to bring them in. So the example of working with students as well, I think, is super useful for that.
I mean, on site right now we have I think 37 trained engineers, who can access the kit at any time. And a big part of that is failure. So rather than hand-holding all the way through, it's, you know, come use the equipment and watch it fail, and then next time you'll understand, you know, how to support that, or choose a different material, or whatever it may be. Yeah.
I think that's so important, certainly. I'm going to hand over to Patrick, who I think has a hand up with a question on the list.
Hi.
Thank you, Candice, and thank you, Mark, for the presentation. I think it was very inspiring. I have another question more on a design side of things. I think you show an artistic picture of one of the components that you have designed and made in 3D printing for a motor.
Yes.
And you show that it that is a very complex shape and component. So what I'm curious about is, how did you design it? So what was the process that took you to reach that very complex design? Where did you start? And
yeah, so I mean, in terms of the actual design itself, that was down to a couple of engineers and some of the simulation guys. So there's an airflow that is required to pass through this jacket to cool the motor and take heat away from X amount of watts, or whatever it's passing out. So that's where it started, simulation. A lot of the more high-end examples start at simulation level, especially when it's to do with heat exchange, especially at that point. And then from there, I'm more involved. They're showing me what they need, what they believe the system should look like. And then from there, it's this just design for additive and implementing that. So for example, those small pillars you see at the bottom, it's coming up with a geometry, again, that doesn't interrupt the flow too much, but provides support to the inner and outer skin in a way that you can actually print it. But also the tolerances on the other side are in line. So it's a multi-stage, multidiscipline process. For exchanges, always starting with analysis. For vibration dampening, a little bit harder. That is, what do you use at the moment? What do we have close to that? Let's see if we can try and benchmark against something that's known, like a polyurethane or whatever. And then from there, it's introducing some more complex geometry, maybe some sort of lattice structure infilled with a pourable resin or whatever it is. But I think that world is, I'm not going to say black art because it's very technical, but you really have to print and test and get those physical results straight away to make that change.
There isn't a tool yet that allows you to create a simulation, and then it allows you to simulate virtually and then understand how the component behaves. I think there are some. I think there are some tools, but I don't think they give you like the answer. So when it comes to, in my experience so far, vibration dampening is all about trial and error, and we've got scientific methods of the trials, and we can get data from that and make changes from that. But it's much easier to go in there and try things out. Yeah. Thank you.
Okay.
I think that's a really interesting perspective, actually, the idea that sometimes we have really good tools that we can do all this simulation and be kind of very comfortable that what we're going to make is going to do the job. And actually, as an experimentalist, I love the trial and error aspect. And it's always an educated trial, as you say. It's based on something, but actually sometimes that is. And perhaps that's one of the challenges for the future, is building up those tools in other areas. We do have one question in the chat just before we finish, asking about opportunities AMRC provides for postgraduate students who want to do things with advanced manufacturing technologies.
Yeah, actually, we had some postgrads come around the other day for a visit. I think, there's obviously a right channel to make that happen. I think perhaps on the AMRC website, there's a main contact, and you can probably just go through that. But yeah, it is something that happens. We have an IDC centre where postgrads do research in part with partners here. So yeah, that is a thing. Yeah.
I would also encourage, having been up to AMRC quite a few times, I would encourage anyone who's not been, if you happen to be in the area, see if you can get a visit. They do much more than just additive manufacturing, huge amounts across manufacturing in general. So Yeah, and I don't work for them, so I'm not paid to say that. But I would encourage everyone to have a look, because it is a very nice facility, and there's something really interesting for everyone to see there. So Mark, thank you very much. That was great.